Friday the 27th of March, and this is Nighttime Mathematics Radio. Forward the show's the same as always. You tweet your questions to @NightMathRadio on Twitter. I'll try to answer them right here live on the air. So before we get started, let's take a minute or two for people to get their questions in on Twitter. Then I'll try to answer them on the air. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Once again, you can tweet your questions in to @NightMathRadio on Twitter. I'll try to answer them live here on the air. For the moment, let's try to answer some interesting questions that came in between two of the shows. And these are questions about images and kernels of linear transformations. The question is, if I've got some matrix, and boy, do we have some matrices here for you. Let's see if we can find the kernels and images of these matrices. And let's talk about what they are, because these are interesting and important concepts. Let's take a look. So let's start with a really simple matrix. Here's one of the easiest matrices you could possibly imagine. We have 1, 2, 2, 2. Call that T. So what is this thing? This is a matrix that takes a two vector in, because there's two columns, which means it takes in a 2 vector, and it spits out a 2 vector because there's 2 rows, so the output is also 2 vectors. So this takes you from R2 to R2. In other words, this takes you from points in the plane to other points in the plane. Cool. Now, the question we're asked here is, can we find a basis for the kernel and a basis for the image? Well, let's see. To find a basis for the image, you have to find a set of linearly independent basis vectors on the thing of the columns, because what can come out of a matrix like this is some linear combination of the columns. Because what happens when you multiply this by some vector, say AB, is you end up with the first column, 1, 2, times A, plus 2, 2, times B. So this is a really useful way of thinking of what a matrix multiplication is. Because after all, if you think, how do you get the top answer? Well, it's 1 times A plus 2 times B. That's the usual way of doing matrix multiplication. What do you get in the second column, second row rather? Well, that's 2 times A plus 2 times B. So that's just some combination of this vector and this vector. And the cool thing is, these are very clearly linearly independent, because after all, if this is 0, if this is equal to 0, then we have A plus 2B is equal to 0, and also 2A plus 2B is equal to 0. So subtracting the second equation from the first, you get A equals 0. And then back substituting that in, you can immediately get 2B is equal to 0, or B is equal to 0. So this actually tells us two things. First of all, these two vectors are linearly independent, which means that these by themselves are a basis. So the image space, that is, the possible outputs, are just the span of these two vectors, 1, 2, and 2, 2. And the second question is, what's in the kernel? And the answer is, we can actually see that here. What is the kernel? The kernel is, what can you possibly plug into this vector, this matrix rather, and get 0 out again? And we just checked that in the answer, because it turns out the condition for linear independence is exactly the same as the condition for... It's exactly the same as what you do when you're looking for a null space. Because remember, you're looking for a null space, you say that's equal to 0, 0. And if you're curious if these two things are linearly independent, you say, well, what does it take for these to be 0, 0? And those are the same thing. And since in both... So in this case, we learn immediately that the kernel of T is equal to precisely 0, 0. It's just the 0 vector space. There's nothing else in the kernel here. And that makes sense. Why? Because this matrix, depending where you are in linear algebra, is invertible. What that means is, if I set up a system of equations like I did here, and put absolutely anything here and here, I'll be able to solve it. That means this is an invertible matrix. This is for any point I want to get out, there's exactly what put in. In other words, this mapping is 1-to-1 and onto. And therefore, the kernel is not trivial. Let's look at a more interesting case. Let's look at this matrix. -1, 2, 2, 2, -4, 2. Now, this is a 2x3 matrix. This has 2 rows and 3 columns. What that means is the input space is a 3 space. It's like points in a space. It's triples of real numbers, like 1, 2, 3, or 1/2 pi e, or whatever you might want. And the output space is only R2. So we know these 3 column vectors cannot be linearly independent. Because after all, they're all 2 vectors. You can't have 3 linearly independent 2 vectors. Because the space of 2 vectors is only 2-dimensional. So what are you going to do here? Well, the usual trick, if you want to find... Let's start by finding a kernel. How do we want to do that? And the answer usually is we want to put this thing into what's called reduced row-echelon form. Let's start by getting into row-echelon form. What row-echelon form is it's actually a formalization of what you learned to do when you were first taking algebra with systems of equations. Because way, way back, if you set the Wayback Machine on your head, way past before algebra had a cool linear in front of it so that you could impress the cool kids and not have elementary school students shaking their heads sadly at you when they see algebra textbooks. You took a class called algebra in high school, and when you took that, you learned something called method of elimination, where you sat down and tried to eliminate variables from other equations by adding or subtracting multiples of rows. And that's what we're going to do here. That's how you get to reduced row-echelon form. What reduced row-echelon form is this. Basically, you start by saying, let's look at the upper left corner of the thing. We'd like this first row of the matrix to start with 1. Well, how do we do that? Well, one thing we're allowed to do is what we'd like to do is multiply this row by -1, because that'll put a 1 in that first position. And it turns out there's a matrix that'll do that. Because you can multiply this matrix from the left by what are called elementary row operations. And the cool thing is we've always been talking about multiplying over here on the right by a 3 vector to get to our 2 space. But we can also multiply on the left by a 2x2 matrix. This will apply another transformation to this thing. So we'll say -1, 0, 0, 0 times -1, 2, 2, 2, -4, 2 is equal to... Well, let's see. That's -1... Oops, 1 here, not 0. We don't throw away the second row. What this says is -1 times the first row will be the first row afterwards. 1, -2, -2. And 1 times the second row will be the second row afterwards. 2, -4, 2. Now what do we want to do? Well, now we want to eliminate everything else in this column. Everything else's column is just a 2 here. So what we want to do is subtract twice the first row from the second row. Well, it turns out there's an elementary row operation for that. This time, the first row of this I want to leave alone, 1, 0. The second row I want to be equal to the old second row minus 2 times the first row. And then I'll multiply that by the same things we had before. Minus 1, 0, 0, 1. Minus 1, 2, 2. 2 minus 4, 2 is equal to 1 minus 2 minus 2. 2 minus 2 times 1 is 0. Minus 4 minus 2 times the minus 2 is 0. And finally, 2 minus 2 times 1, and let's see if we can do this one now. 2 plus minus 2 times 2 is 6. Okay, we've got another, we now have this 6 here is now the first element in its row that isn't 0. We want to turn it into a 1, so this time we're going to divide the second row by 6. That's easy enough. We say, okay, once again, leave the first row alone, and multiply the second row by 1/6. 1 minus 2 minus 2, 0, 0, 1. Now at this point we're in something called row-echelon form, because you can see that in each row you have a bunch of zeros followed by a 1. The ones stagger out to the right, and below every 1 you have nothing but zeros. Or rather, to the left of every 1 you have nothing but zeros. But let's make things really easy. Let's go to a reduced row-echelon form, where every 1 is in a column all by itself. So to do that, I'll say, now, for one last step, I'm going to turn the first row into the first row plus twice the second row. First row plus twice the second row, and I'll leave the second row alone. Missed one? Oh, I missed one. 1, oops, minus 2, 0, 1. This should have been a 1 here, so 1. Minus 1, 0, 0, 1. Minus 1, 2, 2. 2 minus 4, 2 is equal to 1 minus 2, 0, 0, 0, 1. Great. This is reduced row-echelon form. Why is reduced row-echelon form useful? Well, how would we find the kernel of this matrix? Well, we'd say, if we find the kernel of this, we say, okay, let's find an ABC such that this times ABC is equal to 0, 0, 0. We can solve that as a system of equations. The cool thing is, if this is true, if this times ABC is 0, 0, 0, each of these operations here, each of these elementary row operations is invertible. There's an obvious inverse. Here, I added twice the first row. I added twice the second row to the first, so to undo it, I subtract twice the second row from the first. Here, I divided the... Oops, 1/6. Here, I divided the second row by 6, so to undo it, I'll multiply by 6. Here, and so on and so forth. Every one of these elementary row operations is an invertible operation, which means I can apply their inverses one by one, and show that if something's in the kernel of the matrix in reduced row-echelon form, it also is in the kernel of the original matrix. But it's way easier to solve this system of equations. After all, we've already done all the work you would do in an elementary algebra class. But it's even better than that. Because first we can do that and say, okay, great, so a minus 2b is equal to 0, and c is equal to 0. So if you're in the kernel, you have to be of the form. So this tells us that A is equal to 2B. So 2, 1, 0 times A. So in other words, the kernel is just the span of 2, 1, 0. But it's better than that. Why is it better than that? Because remember, as we were talking about in the first problem, the work you do to find a kernel is the same work you do to see whether rows are linearly dependent or not. So with that, in particular, after we ground through this thing, we found that the first column and the third column ended up being what are called pivots. They ended up being the ones that have 1 in them, which meant that we couldn't eliminate them just using the vector we already had. Why is that useful? Because it means the same the same columns of your original matrix are linearly independent. And that takes a bit of proving, but you can show it. So in this case, minus 1, 2 and 2, 2 span the image. So in this case, we have some interesting answers. We have kernel of T is equal to the span of 2, 1, 0. And the image of T is equal to the span of 1, 2 and minus 2, 2. Notice that these have different dimensions. The kernel is a 3 vector. Why? Because it's part of the input space. The kernel the kernel is the linear space of what inputs can I feed to my matrix to get 0 out. The image is the output space. That is, what is the linear space of things that can come out of my transformation? And there's a very famous theorem called the rank nullity theorem, amongst many other names, that says that the dimension of the kernel plus the dimension of the image add up to the dimension of the input space. And that's what we see here. We have a 3-dimensional input space. It has a 1-dimensional kernel. It has a 1-dimensional kernel and a 2-dimensional image. And you'll see that holds true in every one of the problems that you do like this. That's really a useful property. What that tells you is linear transformations, in some sense, produce all the structure of them is in vector spaces, either in the input space or the output space, or it's in what are called linear subspaces. That's linear subspaces are part of a bigger linear space. The kernel here, we've got this nice 1-dimensional, essentially a line going out in the 3 space, going through the origin. That's things that will map to 0. And the image space is a 2-dimensional space, and since it's a 2-dimensional space in R2, the image is all of R2. So actually, the moment we saw a 1-dimensional kernel, we could also just as easily have said the image is the span of 0, 1, and 1, 0, because after all, if you have a 2-dimensional subspace of R2, there really only is one. It's R2 itself. This is Nighttime Mathematics Radio. Well, that was a good long topic. It's Friday afternoon. I think everyone's tired. Let's take 2 or 3 more minutes to see if anyone comes in on Twitter with any more questions, and if not, we'll end the show. This is Nighttime Mathematics Radio. Welcome back, everybody, and I think it's time to say goodnight to this week. It's been a good long week. I've gotten a lot done. But the math homework keeps going on in this strange world with no schools but tons of homework. So if anyone has any more math questions, feel free to tweet them to @NightMathRadio on Twitter. I'll try to get to them in future shows, and of course I'll try to respond on Twitter as well. For the meanwhile, this has been Nighttime Mathematics Radio. Thanks to everybody. See y'all next week. Good night, all.